And it's going to be a bit more technical than the first one, but it's not going to be kind of scary technical. It's just going to mention a few technical things. I'm afraid I tried to make the kind of talks separate so that somebody coming in now could follow my speech. So it might cover a bit of the same ground covered in the previous one. Probably not too much, though. Okay. Again, I have a content slide. I'll start off by mentioning a few design issues in developing the Linux kernel. Then I'll mention the basic design behind the system, how development actually happens a bit. Then I'll take the three parts I consider mine, the process management, the file system code, and the memory management code. I'll look at them a bit. They are actually not even the largest parts of the kernel, but they are kind of the basic blocks and the ones I keep most under wraps and do most of the things myself. Then finally I'll take a look at some of the work in progress right now in the kernel coding part of the kernel. Okay, design issues. The first one is keep it simple. As everybody who has written a kernel knows, writing kernels is not very simple. There are lots of complications that don't necessarily exist in other programs. So if you want to get something that works, you want to keep it very simple, and to do that, you usually have to kind of leave out the bits that look too complicated, or features that might be nice but that require too much complexity of the rest of the system. On the other hand, I did want to have a very compatible system because, well, I enjoy writing kernels. I don't enjoy writing editors and compilers and shells and so on. So I wanted to have this part of the Unix system ported over directly with minimal amount of work so that I could go on writing the actual kernel. So Linux tries very actively to be as compatible as possible, even if that does mean some problems then because of brain damage in the original design and so on. There are actually pretty few of them. There are brain damages in some added features, but that's okay. We can just keep the features we don't think are worth it. Also, I'm a performance freak. I actually compile the kernel into assembly code every once in a while just to look at what the compiler says, and if I don't like the output, I change the C code to compile better. This may result in kind of weird code because GCC is not optimized for the kind of architecture Linux is running on, especially the lack of registers lead to kind of bad code. So if you actually look at the Linux code, you'll see that I sometimes do things a bit non-intuitively. It might be due to my weird coding standards, but it might also be due to the fact that it results in better code when compiled. Also, the thing about maximizing performance means that I don't want to penalize hardware that's good. So if you have lots of memory, I want Linux to take advantage on it. This may sometimes mean that Linux doesn't run quite as fast on small machines. Also, if you do have a math coprocessor, as I do, I want Linux to take full advantage of it. So unlike some other systems which use software floating point by default, Linux uses hardware floating point by default and then lets the emulator take care of it. I dislike intensely systems like, well, some Spark stations where the compiler by default starts using the soft floating point when it knows that the hardware can't support things like square roots and so on. And then when you move over the binary to a better machine that does support square roots, the code doesn't run as fast as it should. So I like to get the most out of a machine if it can do it, and if it can't, well, tough luck. Linux still gets pretty good performance even on a low-end machine, so I try to also keep it's usable even when you don't have a math coprocessor or just 2 megs of memory. Also, the final thing is I don't want to add a feature which may turn out to be hard to keep up. So I don't want to add limits or things that could limit future expansion, like the 640K limit in DOS. I try to avoid those. This means that some features people have asked for and that could be easy to implement, like, for example, people have asked for a PC direct access to screen memory in order to be able to write curses type programs with menus and so on easily. And I don't actually want to support that kind of thing because it then doesn't port to different machines at all. So I try to avoid things that lock us to some design. What this has resulted in the kernel is the keep it simple design resulted in a monolithic kernel. This is something of a debate in the operating system community. The microkernel people think that microkernels are easier to write, and I disagree strongly. I think microkernels are harder to write, especially if you don't have anything to start up from. Monolithic kernel may have some problems in keeping up the code and upgrading and so on, but it also makes it much easier to actually change the internals of the kernel completely without having to change several different subsystems, which may happen in a microkernel. I'm biased. The first kernel I used was Minix, which purported to be a microkernel and did it horribly badly. So instead of having modularity due to the basic design of the kernel like a microkernel does, I've tried to make Linux reasonably modular so that there are separate subdirectories for all the major codes, major pieces of the kernel and so on. Also, when something looks like it could be ugly to implement, I'd rather skip it than trying to implement it. To make a kernel easier to program, especially because the two major problems in writing and operating systems may be race conditions and deadlocks due to locking. So what I did, and what the original Unix did, was make the kernel non-preemptible. So when a process runs in kernel mode, no other process will preempt it unless the process yields control voluntarily. This leads to a code that doesn't need any locking on internal data structures, because you know you're not going to be interrupted by some other process. You still have races when it comes to actually interrupt handling. And then you have races when you try to access user code data which might be swapped out, or when you try to do some I/O. But those races you at least know about much. They are more dependable. You know when an interrupt can change your data structures, and you also know when you actually access user code. The basic design, which is one of the problems right now, is that the whole kernel is kind of non-portable. It's less so than it was at one point, but still it's about 176,000 lines right now, which is, it's not the smallest Unix kernel around, but it's still pretty small. It compiles in about 10 minutes if you have a reasonable machine. And of that, almost exactly half is device drivers. It's actually within a line or two right now, which is just because the PC hardware has so many different devices. So it's kind of naturally machine-specific, the code, but also some of the design decisions I made early on were kind of bad in making it portable. So I expect to have some problems in porting the memory management code to a 64-bit machine and so on. On the other hand, the memory management code right now is less than 2,000 lines, if I remember correctly. So porting that isn't too bad. Okay. The development framework is kind of set out by the fact that the whole development of Linux is completely open, and I put out my latest version of the kernel about every 2 days or so. The latest version right now is 1.1.12, which I put out the day before I left for New Orleans. The alpha versions like this one, which I put out, may not even compile, and in fact 1.1.12 doesn't link unless you add a line to a make file. But this does mean that people can test out my version, my latest version, and do changes against that, and interactively kind of see all the changes done to the kernel in the last few days. To kind of control the problems that arise when many different persons work on the same sources, there's a coding style standard, which is essentially that all code has to be ANSI C, and the bracing style is the one true bracing style, i.e. the one used in the original Kernighan and Ritchie book. I'm not religious about this, so when I get a driver, which I know I can't keep up, I don't change the actual formatting. But the kernel, for example, is always compiled with all warnings enabled. And if I get a warning, I know something is wrong. So there's kind of type checking and so on, which helps avoid some of the problems you'd otherwise have with several persons working on the same sources. Also, due to the fact that major parts are in different subdirectories, I can, for example, concentrate on the ones I consider mine, i.e. the kernel, the FS, and the MN, memory management subdirectory. And people who write device drivers, for example, there's a separate driver subdirectory which is partitioned into character drivers, block drivers, and SCSI and sound. So people can actually give me a whole packet which contains a new driver, and I don't even need to know about the internals of it because it just fits in its specific place. The other thing, the main benefit of actually having this kind of open development is the fast feedback from developers. You get fast feedback from the users too, but it also means that when a developer sends me some patch to his driver or similar, I can put it in the same day, maybe make a new version the next day, and then the developer knows that, okay, Linus put it into his latest kernel, now I can forget about these old problems and concentrate on the new ones, which sadly there always are new ones so far. What this means in practice is that I'm at kind of the top of the hierarchy of developers, and under me I have a few trusted kernel developers. There is one person who mainly handles the networking side of Linux. There's one person who mainly handles SCSI drivers. There's one for every file system except for the Minix FS, which I wrote myself, and so on. So these are kind of trusted in their own areas, and under them they may have a few more which they trust to do minor patches to that part. And the patches then go from downwards up to me and then into the standard kernel. This is not a core team-like hierarchy used in X386 and so on, because outside intervention is actually encouraged and appreciated, so you don't have to be a recognized developer to actually send me a patch. And I do get patches by almost, I do get patches that are kind of 2 lines of patches which fix a small problem by somebody I've never heard about before. And if it's obviously the correct patch, I use it. So it's not a problem if you aren't a recognized developer. Okay. I'll take up the process management part of the kernel. I don't know if process management is actually the right word. Maybe something like basic building blocks. It's the kernel subdirectory of the Linux kernel and contains all the really low-level details about the machine, except for the memory management, and handles interrupts, exceptions, and DMA and so on. So when a driver wants to use some interrupt, it asks the kernel, could I have this interrupt? Could you redirect it to me? And then the kernel decides if maybe some other driver already has that interrupt. Also, the process management actually does contain process management, so it takes care of any system call requests a process may do. It also takes care of any process faults. So when a process tries to do something that's illegal, like disable interrupts, the kernel notices this and kills the process off. There's a separate file for handling the virtual 86 mode in the 386 processor, which is used by the DOS emulator and possibly in the future the Windows emulator. There's also the Linux kernel by itself uses the flat address space of the 386, so it actually has only a code and data segment which cover the whole address space of the process, but the process can ask for segments, and the kernel will give it within reason up to 512 or something like that segments it could use if somebody really wants to use a segmented architecture. This again is used mainly for Windows emulation. Okay, I'll actually give a programming example of a I don't know how different this is because I never saw real Unix source code before starting on Linux, and after starting on Linux, I've actively tried to avoid it. Plus, it actually would take too much of my time, so it hasn't been a problem avoiding it. But traditionally, in operating systems, the actual action of going to sleep or scheduling a process is closely tied to the state the process is in, which leads to some problems. You have a special call which is, please now I'd like to sleep on this special action variable or whatever, which leads to race conditions because you usually have something like this. You have if some empty okay. This is just to give you an idea. You have code that says, if this buffer is empty, I want to sleep on it until it's filled again. Now, this looks simple, but has the problem that between the test and the sleep, the buffer might actually get filled. Then we'd sleep on something that will never happen again. To handle this, you have semaphores and event counters and so on. But and I knew of these, but I actually decided on a completely different solution, which was to have separate process state and scheduling primitives. So you have a process state which the process can set by itself. Here, the current process says that now I'm sleeping, but what it actually is doing is it's lying to the kernel. It's not going to sleep at all because the scheduling is separate. Then it tests for the event. In the example, this would test if it's empty, we sleep. What this add wait queue and remove wait queue are doing is setting up the information to tell whatever routine that fills the buffer which process to wake up. Now the race condition is completely gone because if an interrupt comes in here, the interrupt will notice the event queue and wake up, change the state of the current process, and the schedule will do nothing at all. So now we won't sleep on something that never happens. You may know, is this done in any other operating system like this? Okay, nobody knows. This is actually has the added advantage that sleeping on several different events is a natural extension of this, which is not as easy if you have a sleep call. If you had a sleep call which goes to sleep, you can't put many of them after each other because the first one will go to sleep. So this actually works very well with the select semantics I mentioned earlier. Others do it other different ways. This was just an example. Okay. The other major part I'm personally responsible for is the file system code, which actually what it does, it virtualizes the file system interface and doesn't know anything about the file system at all internally. It just looks at the requests the user makes, and then translates this into the appropriate internal virtual file system interface calls. Unlike at least BSD 4.3, which used a special inode for a normal file, and then a V node for a virtual file over NFS, for example, Linux doesn't have separate inode V nodes. Linux just has V nodes, and then, well, we call them inodes because why not? They are the only thing we have. And then lets the lower level file system stuff handle it any way they want to. I think 4.4 does it this way too, I'm not sure. What this allows is kind of the basic blocks for any file system are in the VFS layer, notably buffer cache handling, some name lookup, the basic Unix semantics for mounting a file system, and so on. And then we have separate modules that actually implement each file system. And Linux has no native file system at all. All file systems are equal. It's kind of a communistic system in that way. The actual low-level file system components right now, there are 10 of them, are the one we call native Linux, which is the second extended file system, which allows long file names, big partitions, I think up to 4 terabytes in size, file sizes of up to 2 gigabytes. Then there's XFS, which is similar but slightly different. NFS, the Minix file system, which is the original one, which is the same one as in the Minix operating system, which I used to copy files over. And then System 5 file system, which can mount Xenix, Coherent, and some other System 5 formats. More non-Unix file system type is the MS-DOS file system. If you do use MS-DOS, you can just mount your MS-DOS partition or floppy or whatever, and it looks like a Unix file system to Linux. Of course, there are limitations like 8 characters a dot and 3 characters, and then you don't have any separate protection rights. Those are set up at mount time and are the same for the whole file system, so on. There is also a OS2 HPFS file system. This one is currently read-only. You can't write to the OS2 partition, but you can read your files from it. And there is the Cd-Rom ISO 9660 file system used for most Cd-ROMs. It has the Rockridge extension, so you get long file names and symbolic links and so on. There's a third file system. Somebody called it the most fun you can have with a file system, which is the virtual Proc file system. I got the idea from what I've read of Plan 9 and tried to get the best things of that. It turns out that System 5 Release 4 also has a Proc file system, but don't confuse the Linux Proc file system and the System 5 version, because the System 5 version is totally brain dead and useless. The Linux Proc file system is actually extremely useful, and we've made away with all the kernel memory hacking you needed to do for processes like PS and who and uptime and so on. They just read the virtual file system, and if you don't have an uptime binary, what you can do is you just cat proc uptime, and you get how long the system has been running in seconds, so on. The actual uptime binary then prettifies these to days, hours, minutes, and how many users there are on, and so on. The Proc file system is completely internal to the kernel, it doesn't exist physically at all. You just looks like a file system. Other file system there's been talk about and have actually been implemented is a Ftp file system, which looks like a file system, but when you do get a file, it goes through the FTP protocol and gets it from some other site. This is possible done actually as a user level file system, but it's not in the default kernel, and I wouldn't trust it myself. Stunt, if I understand correctly. Okay, this is just, you won't do much with that. It's a list of all the functions you need to implement in order to create a file system. In fact, you don't need to implement them all, but they are divided into 3 levels: file operations, enode operations, and superblock operations. This allows you to do just a subset of the virtual file system code needed. So for example, unnamed pipes, which don't have any other semantics than the file operations, they actually don't even have the higher level VFS interfaces at all. The perhaps most interesting part of the Linux kernel is actually the memory management. It's also one of the smallest parts, but as memory is such a fundamental resource in a Unix operating system, in any operating system in fact, you want to make the fullest possible use of the memory you have in a machine, especially on a PC where you may have only 8 megabytes and Emacs takes up all of that. So when you have both the kernel wants memory for internal resources like a buffer cache and for internal data structures like the enodes and files. The user processes wants memory for actual code and data. Well, I took up to mention the file buffering already. Also, there's shared memory, which then acts differently than from normal user memory. And to maximize and optimize all this, I've tried to minimize free memory. By definition, free memory is useless. You don't do anything with free memory. So while some other operating systems try to keep something like 10% of the memory free for potential use, Linux actually tries to keep something like 100 kilobytes on a 60 megabyte machine, which is kind of panic memory. If some interrupt needs memory now, it has 100K to use. This is mostly for network device drivers, so when a packet comes in, it can ask for this limited resource. All other memory is then used for either process memory or for buffers. So if the machine in this building is still up after this, you can go and look at it and type the free command, which shows how much free memory you have. It had 32 megabytes of RAM. When I installed Linux, it used 28 megabytes of that for buffer space to speed up operations. Now when it's running X and whatever, the buffer space automatically shrinks, and only probably something like 7 megabytes or so are used for buffers. Just minimizing free memory isn't good enough. You can minimize free memory by just using it up. You can minimize free memory by starting up Emacs. So, to actually maximize the use of memory, you want to use memory efficiently, preferably in a way that you actually use the same page of physical memory several times. So Linux not just shares memory by copy on write between processes which have forked, it also shares memory with processes that share the same executable image or share the same shared library. It even shares memory with the buffer space, so the same physical page could contain the buffers for an executable. It could also be mapped into several different programs as actual code. And again, if you use the free command on the PC, Linux PC here, you usually get something like 8 or 10 megabytes of shared memory, which doesn't mean that it's shared like in System 5 style IPC shared memory. It just means that Linux noticed, okay, all these processes and this file system buffer cache are actually having the same data, so we just use one physical page for it. On my home machine, this means that I have 16 megabytes of physical RAM, and actually the kernel maps in about 24 megabytes of virtual memory at the same time by using, that's 50% larger than you actually have in the machine by just reusing the pages as much as possible. Okay, we're again getting close to the end, and I'll just mention a few things I'm working on and some other developers are working on. We're working on kernel threads, which I'm not actually sure if it's a good idea, because some timings have indicated that if you can thread in user space, it's usually much faster to do task switching and so on. So for some applications, you don't actually want kernel threads, because kernel threads then have to take they have to be so general, you automatically have to save more registers and so on. On the other hand, kernel threads are useful for lots of things, so we're still going to implement them, if only because it's an interesting idea. What this actually means is that we're separating the process structure, which has been one large structure, into separate file system, memory management, and register task parts, which allows different threads to share the same memory management, or maybe have different virtual memory but share the same open files, or share the same root inode, and so on. What's also being worked on, and is actually in the 1.1.12 kernel, is an extended memory management which allows better use of physical memory. The earlier Linux kernels had the problem that all memory management was done on a page-by-page basis, and all 3 pages were essentially on one long linked list, which made it very hard to allocate physical contiguous memory of more than 4 kilobytes, which is the page size on the 386 processor. For most applications, this doesn't matter, because physical memory, you can always map it in contiguously several different pages for user space applications, for example, but DMA and some other applications actually want the physical memory to be contiguous. So we wanted to allow a possibility of allocating larger chunks, currently 128 kilobytes, which is the DMA limit on the PC, at one time physically. Also, what I'm looking into but haven't even started on yet is optimizing the file system. It's currently works well and is pretty efficient, but at least the BSD crowd seem to imply that file name caching might improve performance noticeably. That's one thing I'll look into. It shouldn't be too bad, but I also would like to make it general enough that you could actually use it for things like NFS, which requires that you have timeouts and so on. Also, just the file system cache in Linux is quite advanced in that it grows and shrinks dynamically and can share pages with user pages, but we're still looking into improving it further. It's kind of awkward because it uses the original Unix way of indexing file system buffers by the device and the buffer number they are in, while it would be more efficient for the actual file system to index them by the enode they are associated with and where in that file they are. So we're looking into changing that. Also, what's already there to some extent is loading kernel modules at runtime, so you could load a new driver. This is already used for the floppy tape driver, which isn't part of the standard kernel, but you just get a separate module, compile it, and link it in. We're trying to make this more general, so eventually all kernel drivers will be loadable. So you could do a kernel which unloads the drivers as it notices that the device isn't there and so on. Also, as was mentioned in the previous talk, we're porting it to different architectures. The 68K port did show some problems. On the other hand, it didn't turn out to be too bad. But the 68K is actually pretty close to the 386 in that it's a 32-bit machine and has very similar memory management. Porting to other architectures will probably show a lot of other problems in the Linux kernel in this area. That's it, I'm afraid. And thank you for me. Are there any questions? Yes.
John West, Digital Systems Consulting.
Yeah, could you speak up?
John West, Digital Systems Consulting. Are there any plans for a compressed file system?
There are patches available for a compressed file system, and I've heard some horror stories of it. And frankly, my personal opinion is that it doesn't pay. Others who have smaller disks seem to disagree. We'll see. I don't like the idea because it makes demand loading kind of hard. That's an issue you can resolve, but it has problems. Okay?
Jay Beavers, University of Alaska.
Yeah.
I was wondering if anyone's working on the Andrew file system for Linux.
I don't know if I can talk about that. Actually, Andrew file system is proprietary, but we're working on extending the modules interface enough that it could be used as a loadable module. I'm not certain I like the idea about linking in proprietary stuff like Andrew file system into Linux without having access to the source code. But I also know that it would be so useful for the MIT people that I'll probably allow it anyway. From what I heard, the Andrew file system is already ported, and the person working on it, who has been an active Linux user for at least 2 years, is now looking into the loadable interfaces and is optimistic about it. They're using it internally at MIT in at least some machines, as far as I know. Okay?
Reese Pollock, the Wollongong Group.
Yeah.
Given that your first language is different than my first language, having not seen the sources, are the comments and the variable names and such in English or another language?
Yeah, they are all in English. I actually, when I code, I think in English. And while my pronunciation may be kind of weird, I actually read most of the stuff I read is in English. So I think fluently in English, but I just talk it funny. Okay?
John West, Digital Systems Consulting. Is there an implementation of DCE for Linux, or do you know of any under development?
I have no idea at all. Is Motif part of DCE?
No, DCE is another proprietary.
Okay, it's proprietary. Probably not. Okay, please, 10 minutes or more questions, and we can skip this.
Otherwise, I'd make him tap dance.
Yeah.
Well, I mean, there is
We'll draw. Just wait. Are you nervous? Do you feel lucky? What's your name? I'll pull your card. Oh, you mean in the drawing? Okay.
Okay.
Well, do you want to draw, or do you want to
Okay,
tap
we'll
dance?
draw now.
Actually, let's take a vote. How many people want to see him tap dance?
Okay, good. Whew.
That looked like a
That
majority
wasn't
to me.
half of you. No
Yeah, it
way.
was 3/4.
No way was that 3/4. you want to hold this bag. Check that I don't cheat.
Yeah, well.
Okay.
Hey, that's your card.
Robert Simon, of Principal Engineer of Net Access Products Division, has already left. Okay.
Next.
Who cares about him anyway?
Guess I shouldn't give him all that pop before he came in.
Mary B. Kuklinski. Sorry about the name, I probably
Come on
pronounced
down.
it totally incorrectly. Congrats.
Thanks.
Oh. And Wayne Shirley, engineering specialist from Monsanto. Okay. Congratulations to you. Okay, thank you. Okay.
Okay, now you ready to see him tap dance?
A few more questions and we can skip the dancing.
It's either tap dancing or stripping, so.
Okay, you promised I could wear
know
a bag
what I
on my
wanna
head
see.
if I stripped.
What's that?
You promised I could wear a bag on my head if I stripped.
That's right.
Okay.
We did promise that.
Okay.
Protect your dignity.
Here's a question.
Okay.
I've heard discussion on the various mailing lists and the news groups about a Kerberos implementation. Do you know anything about it and what state it is in?
I'd assume Kerberos shouldn't be any problem, except then exporting it outside the U.S. due to the stupid regulations. But it's not stupid, interesting. Okay. Okay. I don't see that it should be a problem. I haven't looked into it because I'm the trusting kind of guy who doesn't care what people do to my machine. Okay, that's it. No, one more.
A lot of people are asking about it anyway. Can you display on your overhead the phone number for the Linux?
I'm going to the trade show.
Okay. Hyvää päivää.
Hyvää sanoa tervetuloa ja kiitos.
Kiitos itsellesi. Actually, I speak Swedish as my mother tongue, so I'm one of those things.
My parents were born in Finland. I was born in Los Angeles, but I learned some Finnish growing
Okay,
up.
I can actually understand you talking. So I know
Okay.
wait, I'll just. Okay.
Well, I just want to say it was a great talk.
It was.
And I saw you coming up the elevator escalator. The first day I came here and I saw Linus. I couldn't pronounce the last name. And I wanted to turn around, but I was going down. I wanted to shake your hand.
Okay.
I spent the last 3 weeks on the MIT server, and now I think on the hack pictures.
Okay.
I
Good.
I didn't know about the distributions.
Yeah.
And the sunset is probably the easy one to get it all together.
I don't actually know which is easier. I've used Sunset because it seems to be the larger one right now.
Well, I got some good help from some other people here who told me
Okay.
the error of my way.
Yeah. Okay.
How many files can be opened at the
All right. just remove this one. On a per process basis, you have limitation of 256 files, but on a per system basis, it's actually done. So it allocates items as I think there's a maximum number of 2,000, but that's defined somewhere, which is just a simple more as a large chain. If that one is reached, it starts complaining and says something's wrong, probably due to free a file, it should be free or so. So, yeah. And of course, support time for. Yeah, that's really good. How many fonts do you support? How many fonts are there? Well, okay, there's some. No problem. I think theoretical figures for extended fonts. That actually would be 2 gigabytes in RAM. Longest possible file. And then it gets so slow. But there's no problem. I'm not looking to work with that. No problem. It depends a bit. Your average printing machine is usually a PCI machine. Also has the NCR SCSI machine. And the NCR SCSI drive they are not sufficient. Actually, the Pentium is obviously NCR chip is just SCSI controller, but it's a good controller. Same is true of Diamond Bike graphics card. It's a very fast graphics card. It is a full Unix implementation in that it